discrete in the sense because of various kind of confinements in the solid. Now we have a certain range of energy values that the electrons can take and a certain range of energy values that the electrons cannot take. So this allowed energy range that the electrons can take is known as the energy band, and the energy range that the electrons cannot take is known as the band gaps. So this comes in regular sequence. There is a range, allowed range, forbidden range, allowed range, forbidden range. So that's why there are bands, band gaps in sequences. And the solids that we are concerned most in this course is essentially semiconductor solids, or even in most of the electronics engineering, we are concerned with uh, semiconductor materials. And in semiconductor, the most popular semiconductor material is the silicon. It has 14 electrons and in total, and it has 4 electrons in the outermost shell. So, and this is the bonding pattern, roughly, very roughly the bonding pattern. Actually, this is not how it is there in the actual solid. It has a 3D structure. Also, the electrons are not discrete as shown in this particular figure. So we have electron wave functions. Electron wave functions have orbitals are sitting in the orbitals, and orbitals have probability distribution of finding the electrons at various places according to the time. So this sharing by the sharing of electrons, uh, there is this sort of attraction between various atoms of silicon, and that's how silicon solids are formed. Uh, the two other popular semiconductor materials are germanium and gallium arsenide. We will see shortly as well that there is another important property of semiconductor materials uh, that uh, we need to be careful about, and that's what we'll see maybe in coming slides. That is uh, uh, about the relationship between the energy and the momentum of electrons. Okay, but before going into that, we also saw in the last class uh, that at room temperature there are certain electrons in these solids that are free to move inside the solid, and these are known as the intrinsic carriers. Intrinsic carriers mean the number of free electrons and holes, electrons slash holes, available for conduction in the pure material. When the material is pure, the concentration of electrons or holes in the material is known as the intrinsic carrier concentration, and it is essentially the conductivity of the material depends significantly on the intrinsic
Sir,
carrier
please repeat
concentration of the
intrinsic carrier.
yeah. So the intrinsic carriers. So at 0 Kelvin, when the temperature is 0 Kelvin, absolutely zero temperature, all the electrons are bound to their respective atoms. Okay, but at room temperature, because of the thermal fluctuations, because of the thermal energy of the environment, some of the electrons actually gain energy and they are free from their atoms, but they are collectively bound to the solid. So they are no longer bound to a single atom, they are bound to the collection of atoms, this entire solid in a way. And these are known as the charge carriers or the free carriers or mobile carriers. When the material is pure, when we have 100% silicon crystal, when the silicon is absolutely purely synthesized, in that case, this free charge concentration is known as the intrinsic carrier concentration. And the material is known as the intrinsic material, essentially. Intrinsic means absolutely pure. There is no external impurity, there is no external agency uh, influencing the conduction or the electron and hole population in the material. Okay.
Sir, but at 0 Kelvin, we say na कि semiconductors act as insulators. So how then free electrons or holes will be available?
Sorry, semiconductors. Sorry, what
Will
did you
act
say?
as
Can you please?
insulators
Semiconductors will act as insulators when?
at 0 Kelvin.
Yes. So at 0 Kelvin, there is no free carrier in the semiconductors. We are talking about room temperature. So what I said is that at 0 Kelvin, all the electrons are bound to their atoms, respective
So
atoms.
but
So
so but
all
you
atoms
defined
will have four electrons.
so you define intrinsic carrier density at 0 Kelvin.
No, no, no. So, sorry if that is conveyed to you. The intrinsic carrier concentration is defined as at a certain temperature. And in this case, we are talking about the room temperature.
Okay, sir.
So, so at zero temperature, the intrinsic carrier concentration will be zero in semiconductors. It is like insulator. Okay.
Okay, sir.
And another important parameter in semiconductors is the mobility of charge carriers. Mobility essentially means the ease or the uh, or how easily electrons or holes can move around in the material. And more the mobility, uh, more or I would say less tightly electrons are bound to the atoms and easily they can be moved. Okay, and in that sense, gallium arsenide has the most mobility among all these three materials, as we also briefly saw in the last class. So also in semiconductors, there is a notion of holes as well. Do you guys, can you guys define what is a hole basically? How do we define a hole?
Sir,
We all of us
we
know
have
that
never
Electronic
reached
yeah.
zero
vacancy.
Kelvin, then how can we?
Sorry, please repeat. Your question was not properly audible. At
Sir,
zero
we
Kelvin,
have
what did
never
you say?
reached zero Kelvin, then, sir, we have never reached zero Kelvin. Then how can we say that atom would stop if would be at zero
Yes.
Kelvin?
Yeah, you are right. Yeah, technically we have never reached zero Kelvin, but you might be aware that currently in recent experiments at least, we can reach up to few millikelvins, up to uh, and the behavior at few millikelvins is quite close to what we would observe at 0 Kelvin. So we have reached up to 0.00, maybe 1 or 5 Kelvin. And at that temperature, we can see the behavior that we expect at 0 Kelvin as well. Okay. So yes, experimentally, we cannot say what happens at 0 Kelvin, but theoretically, we can say what happens from at 0 Kelvin from our theoretical description of the semiconductors. Also, we have reached very close to 0 Kelvin, and at that temperature, at millikelvins, we can see the behavior that is quite close to the behavior that we expect at 0 Kelvin. Okay.
So holes are electronic vacancies.
Yes, holes are electronic vacancies. Yes, and anything else about holes that you would like to say? That is one. True.
Net positive charge because electrons are not there.
They have positive charge, but how can you say that when the holes are vacancies, how can we say that holes have positive charge? It means it doesn't have, at that place, we don't have anything.
So the net charge is positive because the atom was supposed to be neutral, but because of the loss of the electron, now it has a net positive charge.
Uh, but the electron does not go out of the system. So if we consider the entire solid, for example, if we consider a piece of silicon, in total, the piece of silicon is charge neutral. but still it has electrons and holes. How do you sort of reconcile these two things?
Sir, if we place an electric field and as the electron moves from one hole to another, the holes we can see like holes will be moving in just opposite direction of the electron. So we can say like holes are acting like a positive entity. It's not exactly positive, but it is acting like it.
Yes, sir. They
Yes,
actually do
exactly.
not carry a charge, but they act like positive charges.
Yes.
Sir,
Yeah. So yeah, you are right. Yes. Anybody else wants to say
sir,
something?
holes are used to simplify the motion of bonded electrons that within valence band.
Yes, exactly. Yeah, that is, yes, that is another way of describing holes. And qualitatively, holes are, as you said, vacancies. Holes are vacancies in the atoms that comes about because electrons have now gone away to some other atom, or they are moving freely in the solid. And now, since bonded electrons can also, there are various bonded electrons that can fill those vacancies. So that is modeled using holes. That is true. But when we do the maths, actually, when we do quantum mechanical calculations of solids, so if you ever maybe take a course on quantum theory of solids, you will see that if we solve the Schrodinger's equation and Schrodinger's equation for solid, when there are a large number of atoms put in a proper sequence, uh, I would say like this. So for example, this is a 1D solid. In one dimension, there are atoms placed at a regular sequence at a distance of a from each other, and there are a lot of such atoms. So in this case, the potential energy of the electron will be of this kind, this figure, because these atoms have positively charged nuclei. So let's say that each of these atoms is giving one electron out of it. So it means that there will be a positive, net positive charge of 1 unit on each of these atoms. And when we have a positive charge and a negative charge, an electron in the system, the potential energy of the electron will be the multiplication of the charge divided by the distance between the two charges into constant. And that, if we plot, that will give us this kind of pattern of the potential energy. And if we solve the Schrodinger equation for this potential energy, we will see that the notion of valence band and conduction band comes naturally. There are certain energy values which are forbidden for electrons to take. And at the top of the valence band, we see that the effective mass of the electrons turns out to be negative. So the electrons at the top of the valence band behave as if they are a particle of positive charge or negative mass. Okay, so they behave exactly opposite to what a free electron or electron in the conduction band will behave like. And that's where mathematically this notion. Yes.
The voice was not clear.
Your voice is
Can you
cutting.
explain negative mass?
Yeah, so maybe I'll switch off my video. Is the voice better now? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, so what I was saying is that, let me see the comments. There might be some questions. Okay. Yes, so what I was saying is that when we do the maths in this kind of potential profile, this is the potential energy profile of electrons in a 1D solid, this ux versus x. And in this kind of potential energy profile, when we solve the Schrodinger equation, actually it is extremely difficult to do quantum mechanical calculation for a solid, but we use some approximations, and after making those approximations, if we solve the Schrodinger equation, then we naturally obtain the valence band and conduction band. We naturally obtain certain energy range that the electrons can take and certain energy they cannot take. And the energy ranges that the electrons can take are known as various bands, and the highest occupied band is known as the low band.
Your
And we
voice
see
is
in our
breaking.
mathematical analysis. Hello?
The voice is not clear, sir.
Yeah,
There was a lag.
still not clear? Okay, let me try changing the network. Yes, hello?
Yes, sir.
Yes.
Yes, yes, we did.
Yes, sir.
Is it better now?
Yes, sir.
Yes.
Yes,
Yes.
sir. Yes, sir.
Yes, yeah. So what I was saying is that from our mathematical calculations as well, we obtain that at the top of the valence band, the effective mass of the electrons turn out to be negative. And at the bottom of the conduction band, the effective mass of electrons turn out to be positive. So what it means is that the electrons at the top of the valence band, which means the electrons bonded to the atoms, those electrons behave as if they carry a negative charge or negative mass, one of these things. So they behave exactly opposite to what free electrons in the conduction band would behave. And
So
that's
what does
why
it
So
the
did you just say negative mass?
yes, exactly.
so what does it mean?
Yes, it is. So it means, yeah, so that's why I told you that when you would study uh, the quantum theory of solids, and if we do the maths, there is a notion of effective mass. It is not the same, it is not the physical mass actually. This effective mass is a mathematical parameter, and for a free electron, the effective mass is exactly equal to the physical mass. But for electrons in the solids, the effective mass of electrons in conduction band is positive and the effective mass of electrons in valence band is negative. So please remember that this is not the physical mass of the electrons. It is just an effect. It is just a mathematically defined concept. It is defined to make calculations easier. It is defined to sort of approximate quantum mechanical behavior of electrons by a classical particle. And if we do that, we realize that this parameter called effective mass, it is opposite for both opposite for electrons in conduction band and in valence band. In valence band, it has a negative sign. In conduction band, or at the top of the valence band, it has negative sign, and at the bottom of the conduction band, it has positive sign. Okay,
So can you
and
repeat the negative mass, please, again?
yeah. So what I am saying is that there is this new idea called effective mass. This effective mass is a mathematically defined concept. It is not a physical mass. It is not the physical mass. It is defined to make calculations easier. It is defined in such a way that we can approximate the quantum mechanical nature of electrons by classical particles. Okay. So far,
Yes,
so
sir.
good.
Sir, as you explained about
Yeah.
the
So
electrons in
since
the Sir, as you
yeah, please
explained
go ahead.
about the electrons in the top of the valence band, like if they are acting like they are having a negative mass, so they are loosely held, you can say. So can you give us some similar logic about the electrons in the lower conduction band?
No, so what I was saying is that they have a negative effective mass. Doesn't mean that they are loosely held. It means that they behave exactly opposite to how an electron in the conduction band would behave.
Okay, sir.
So the net behavior of electrons uh, mathematically is different to the behavior of electrons in the conduction band. And yes, for other bands as well, uh, for this actually we need to see the EK relationship, the relationship between the energy and momentum of electrons. Okay, so so for some bands, electrons seem to have negative effective mass, and for some bands, electrons have positive effective mass. But we are generally concerned about only two bands. The reason being that all other bands are either fully occupied or fully unoccupied. So we are not interested in any of those situations. We are just interested in the partially occupied or partially unoccupied bands. The reason being that the conduction only happens in these two kind of bands. Okay. So so in a nutshell, what I wanted to say was that what you said qualitatively, that these bonded electrons will fill the vacancies and the vacancies will move in opposite direction to the electrons. That also comes naturally when we do the quantum mechanical calculations in solids as well. That idea. Okay. More interestingly, you would be you would find it interesting that the mass of electrons is also, or the effective mass, I'm not saying physical mass, and please remember that effective mass is not the physical mass, it is an entirely different concept, it is just a mathematical tool. Okay, so mass of electrons, effective mass of electrons is also variable in the solids. Okay, so I just want to sort of convey to you that this quantum theory of solids is quite an extensive and interesting field. It has many new concepts, and once we do that, these ideas of electrons, all these basic ideas, they become more clear to us. Okay. So yeah, so this we have already seen, and generally the explanation of bands in solids is given in this way. This is taken directly from a book. This diagram, and according to this diagram, when a large number of atoms come close to each other, because of the constructive and destructive interference, it is said that now the bands are formed. And many of you already know this explanation, but this explanation is not very rigorous explanation. This is just heuristic argument. This may not be true as well actually, but this is just a heuristically or this is just one way of explaining this. This is not a rigorously correct way of explaining the bands and band gaps. Okay.
So
So
what
any
is the meaning
questions
of n?
so far?
The
Sorry?
meaning of n in the previous page. Meaning of n previously.
Meaning of N. Yeah, N, it is capital N, you are saying.
Yes, sir.
This is the number of atoms. So what it says is that if we have N number of atoms, silicon atoms, let's say, coming close to each other, there would be 4n electrons in the outermost shell of silicon. Okay? Because the electronic configurations are, because of this electronic configuration of electrons. And 2n electrons will occupy 2n states, and these another 2n electrons will occupy 6n states. When this large number of atoms come close to each other because of the interference, we will have foreign states going down in energy and foreign states going up in energy. And in total, these foreign electrons will occupy the lowermost foreign states, and the uppermost foreign states will be unoccupied. So this upper foreign states will be known as the conduction band, and the lower foreign states will be known as the valence band. And that's why the valence band is almost full and conduction band is almost empty at absolutely zero temperature or at very low temperatures. Yeah.
So what
Yes,
is state?
please. What is state? State is so state means, so as you can see in electronic configuration 1s2, 2s2, so this corresponds to a unique set of quantum numbers actually. One set of quantum number is one state essentially for the electrons. Is it clear? So one set of SMLN is so for example, the in silicon atom, the configuration of electronic configuration will be 1s2, 2s2, 2p6, and 3s2. 1s2, 2s2, 2p6, 3s2, 3p2, right? So this 3s2 and 3p2, uh, so S corresponds to 2 states and p orbital corresponds to 6 states. So, and that is the case in one atom, one silicon atom. If we have capital N silicon atoms, these 3p2 states will be 2n states because there are 2 states in 3p2, and sorry, 3s2 states will become 2n states and 3p states will become 6n states. And this 3s states will contain 2n electrons and 6n states will contain 2n electrons as well, because this configuration is 3s2 3p2. Is this
Sir,
sort
please
of clear?
explain one more. I didn't understand the example of silicon.
Yeah, so this diagram is for silicon atom, and the outermost shell of silicon, the configuration of electrons is 3s2 3p2, right? You remember this? This
Yes.
is basic stuff. So 3s2 means s orbital has 2 states. Okay, so 3s orbital will have 2 states and 2 electrons are there. P orbitals have 6 states. So 3p orbitals will have 6 states and there are only 2 electrons. So in silicon atom, in the outermost shell, in s orbital there are 2 states, 2 electrons, and there are in p orbital there are 6 states and 2 electrons. If we have n such silicon atoms, then we will have 2n 3s states. 3s orbital will have 2n or the all the states or 3s states in all the atoms will be 2n states. They will contain 2n electrons, and the 3p states in n atoms will be 6n states, but they will also contain 2n electrons. Okay, so these things can be better explained on the board. Maybe next time I'll use writing on the screen to explain this. But is it clear, sort of now?
Sir, why p orbital has 6 n states?
So px, py, pz, there are these three possibilities, because you might have studied this in your that is because of the angular momentum and of the s and p orbitals. In s orbital, the angular momentum is 0. In p orbital, the angular momentum is 1. And so that's why there are 3 possibilities, and each the spin angular momentum can be upspin or downspin, 2 possibilities. So in total, it becomes 6 possibilities, 6 states.
Yes, sir. Yes, sir.
Yeah, because a p orbital can contain up to 6 electrons, 3p6, 2p6, like that.
Excuse me, sir.
Yes.
Sir, the foreign states are formed due to interference.
Yes, that's how it is actually generally explained.
Okay, sir.
Hello. So that's how, yeah, that's how it is explained. But I also told you that it is not mathematically rigorous way of looking at this. This is not how it actually happens. The
Okay, sir.
states do not interact in this way. The mathematically rigorous way is the quantum theory of that comes in quantum theory of solids, and that is done when we solve uh, the Schrodinger equation for this kind of potential profile, and in that we naturally see that that electrons collectively in the solid have a certain allowed energy range and certain disallowed energy.
Okay, sir.
Okay.
Yes, sir.
So yeah, so let's have a look at the band structure of metals, semiconductors, and insulators. The metals generally have either a half-filled band. For example, one of the bands is half-filled or semi-filled. It is not completely filled. That is one kind of metals. So in that case, electrons have enough states to move around in the same band. So electrons can easily move around in the same band. So that's why the mobility or conductivity of metals is more. Another possibility, so this diagram shows the conduction band and valence band. The upper band is the conduction band, the lower band is the valence band. The other kind of metals are when the conduction band and valence band are overlapping, which means that in some metals there is no band gap, so to say. So there are various bands, but those bands are overlapping with each other. And that's why electrons have enough states to move around actually. So one kind of metals have either half filled or partially filled bands. Another kind of metals have overlapping bands. And that's why they have easily conducting they are easily conducting system. Electrons can easily conduct in them. That's why the conductivity is more. In semiconductors or in insulators rather, the band gap, the difference between the conduction band and valence band is pretty huge. And even at room temperature, electrons do not get enough energy to jump from the valence band to the conduction band, and that's why the valence bands are the valence band is completely filled, conduction band is completely empty, and no free movement of electrons is there. Generally, the situation is not like this. Generally, in most of the insulators, there are a few electrons in the conduction band. Only a small number of electrons are there in the conduction band. So that's why conductivity is not entirely zero, it is very small. In semiconductors, we have a moderate band gap between the valence band and the conduction band. So at T equal to 0 Kelvin, when the temperatures are very low, in that case, all the electrons will sit in the valence band. They will not move around. There will be no electrons in the conduction band, and the conductivity is zero at low temperatures. But at room temperature or even higher temperatures, electrons gain energy to jump from the valence band to the conduction band, and that's why at room temperature we have some electrons in the conduction band and some states empty in the valence band. And that's why if we apply a voltage around these conductors, the semiconductors essentially, there is some movement of electrons or charge carriers, and that's why there is a finite conductivity. But this conductivity is less than the conductivity of metals, and this is more than the conductivity of insulin. This is just a sort of again a way of understanding conductivity in metals, semiconductors, and insulators.
Excuse me, sir.
Yes.
Sir, can this first type of metal, which is shown in diagram, conduct?
Yes, they can definitely conduct. The reason for their conduction is, you might ask how they are conducting, is that for conduction, actually, what we need is that when we apply voltage or then the electron's energy is changed essentially. Okay. And if there are empty states where the electrons with modified energies can go, then the conductivity will be more, or electrons will be able to conduct inside the system. And that's why in metals, even if there is a band gap, but there are some states which are empty, even in that case, the conductivity is decent. Conductivity is quite good.
Okay, sir.
But we don't say the conduction band and the valence band are overlapping. Like we have read earlier. Hello.
Yes, so in another kind of metals, the conduction band or the various bands are overlapping.
Audio is not clear.
There is lag.
Yes, yeah. Hello,
Yes, sir.
in my audio. Okay, so what I'm saying is that in another kind of metals, the bands are overlapping. So, which means that electrons can easily move around from one band to another band.
Sir,
And
I
there are
didn't get it. Like how the two types of metals exist. Like
so in another kind of metals, type 2, actually, the band structure is not shown here. Maybe I'll put a diagram in the next class. These two bands are overlapping. In that case, there is no band gap in those metals, and electrons in one band can easily go to the second band. Even if a small energy is given to them, they can easily move to the second band. But now you might ask, then why do we have this second band? We can say that there is just one band. Is that what your question is?
no, sir. Like generally we study like the two bands are overlapping, but here in the slide it is shown like metal between in this metal there is a band gap between the two bands. So how
Yeah.
do
So so
these
the,
two
so
types of metals exist?
yeah. So that's why I clarified in the beginning that there are two kind of metals. One is when the bands are overlapping, and second is when the bands are partially filled. Especially the valence band is partially filled, which means that the valence band is also partially empty, and electrons have sufficient states to move around. So this is also the configuration of bands in metals. And
Okay,
the
sir.
reason
Like
for
it
good
is,
conduct
for example, it is sodium. You can say
it is sorry
sodium. Like sodium
sodium.
has a half. Yes, sir.
Why do you sort of think that it might be
So like
sodium?
it has a half filled like a 3s1 kind of half filled orbital.
Okay, yeah, not necessarily actually. We cannot directly generalize uh, from the individual atomic configuration.
Okay, sir.
We cannot say just by looking at the. However, this is that kind of situation. So when various sodium atoms or atoms are overlapping, it is not necessarily true that this will happen. This kind of configuration will take place. This depends on the uh, this depends on the interaction between various electrons. When we put a large number of atoms close to each other, electron-electron interaction, electron-nuclear interaction, on those things, and then once we do the maths, then we see that this is how it is turning out to be. For your, I guess I mentioned this in the last class as well. For your reference, I'll put a sample calculation in on MS Teams so that you can go through the calculations, the quantum mechanical calculation for bands and band gaps. And that will make, if any one of you is interested, that will make these things easy to understand for you.
So basically, like in this metal, like because it is half filled, these electrons in the valence band only can move. So that's why
Yes, exactly.
their conduction is happening.
Exactly. So in this case, they don't need any conduction band.
Okay, sir. Okay.
They can just move inside the valence band.
Sir, you said
Yeah.
that this metal is like partially filled one.
Yes.
So, sir, in that case, both the valence band and conduction band should be partially filled, I think.
Both the valence band and conduction band will be, sorry?
Partially filled. Like same for the conduction band should be there, half partially filled with electrons.
Why? Why do you think so?
I I don't know the reason, but in the NCRT, that's why what I have read. That's why.
No. So that is not the case actually. The thing is, generally, the calculations that we do for very low temperatures. When and at very low temperatures, if we have energy ranges, if we have uh, this kind of band configuration in which there is a band and there is a band gap, then another band, then electrons are filled from low energy to high energy. So once these lowest energy states are occupied, then we put electrons here. Then if these states are occupied, then electrons occupy immediately higher state, energy state. So that way, if the valence band is partially occupied at T equal to 0 Kelvin, and at room temperature, if these electrons do not get sufficient energy to jump from the valence band to the conduction band will be just empty. Okay, it will not be filled.
Okay.
However, if we have uh, enough energy at room temperature for the electrons to jump from the conduction from the valence band to the conduction band, in that case, some electrons will also be found in the conduction band.
So if we apply voltage, will electrons come to conduction band and then conduct, or just conduct between valence band only?
In the case of metals here,
Yes, sir.
yeah, no, not necessarily. If we apply voltage, electrons can conduct in the valence band itself. But if we apply very high voltage, for example, in that case, some electrons may jump to the conduction band as well. But they don't need to go to conduction band for to conduct. In this case of
Sir, I am not getting that why they are conducting in valence band only, because conduction band is that band where electrons can conduct. So how they are conducting in valence band only?
yeah, please don't go just by the name that conduction band means that electrons can only conduct in the conduction band. They cannot conduct. And valence band means that they are bound or they are like valence electrons. Uh, so for conduction, electrons need free electronic states. Actually, that's the only thing that they need. And if the free states are available in the valence band itself, then they can conduct in the valence band. That's not, it's not necessary that electrons need to make a jump to the conduction band in order to conduct. They just need free electronic states and where they can occupy. So if the free states are there in the valence band, they can conduct in the valence band itself.
Okay, sir.
Earlier you explained about the effective negative mass and effective positive mass. So in the given diagram, on the top of the valence band, there is some space, which means is it depicting the negative effective mass?
Here on in the semiconductors?
Yes, sir.
No, it is, yeah, it is not depicting negative effective mass. What it is depicting is that at room temperature or at ambient conditions, some of the so this red means electrons basically. So some of the electrons that were sitting in the that were there in the top of the valence band, they now have jumped to the conduction band. So now they are at the bottom of the conduction band. So it just says that some electrons have now jumped from the valence band to the conduction band.
So, sir, now valence band can also conduct because there are free energy state created.
Exactly. Yeah, and that's where the whole conduction takes place.
Okay, sir.
Even in semiconductors, the conduction happens not just in conduction band, it also happens in the valence band. But in valence band, this conduction is known as the conduction by holes. But it is also electrical conduction. Okay.
Yes, sir.
So if there are free states in the valence band of insulator, then can it conduct?
Definitely, then it will no longer be an insulator. If there are some free states in valence band, its conductivity will be quite good, and in that case, it will not be an insulator. It might be a metal, it might be a, and if the free states are less in number, the conductivity will be less, and then maybe it might be a poorly conducting metal, or it might be a more conducting, a better conducting insulator. Okay. Okay.
Yes, sir.
Yes. So now,
Sir, your
Your voice
voice
is
is
not clear.
cracking.
Sir, your voice
now
is
we
not
Sir,
clear.
your voice is
come
not
to the
clear.
next idea,
There's
and
some connection
I guess this
problem.
idea is not new for you, so we can go quickly. Yeah, there seems to be some connection issues with IIT today.
Yes.
Is it better now? Hello.
Yes,
Yes,
sir.
I see better now.
Yes. Yeah. So as we saw in the beginning of our discussion on semiconductors, that one of the selling points of semiconductors is that we can modulate or we can change the conductivity of semiconductors, and that's how we control the electron flow, or that's one way of controlling the electron flow in semiconductor materials, and it can be easily done in semiconductors. It cannot be done in metals properly, and it cannot be done in insulators. So we cannot change the conductivity of a metal to a very large extent. Similarly with insulator. But a semiconductor, we can change it by a large number. And the method of doing that is known as the doping. Doping means that now, instead of a pure semiconductor, we now have foreign atoms. We now have other atoms that have different electronic configuration. So for example, in this first diagram, in silicon lattice, if we have an arsenic atom sitting or an antimony atom sitting, then this antimony or arsenic atom will have 5 electrons in the outermost shell. Out of these 5 electrons, 4 electrons will be bound to the 4 neighboring silicon atoms, and 1 electron will be left behind, will be free from the bonds, and it will be available for the conduction actually. So this kind of, if we have this kind of doping, if we have an atom which has more electrons than the host atoms, then it is known as, then it causes more electrons in the system, and that's why this is known as the n-type doping. Similarly, if we put an atom which has less number of electrons than the host atoms, for example, if we put a boron atom in the silicon lattice, boron only has 3 electrons in the outermost shell. Then 3 electrons will be bound to the 3 neighboring silicon, and 1 neighboring silicon atom will not have anything to bond to. So there will be a vacancy in this bond. And this causes more vacancies in the system. This kind of doping causes more vacancy in the system. And this kind of system is known as the p-type material, when the silicon has boron doping or maybe nitrogen doping. So not nitrogen, boron doping, or any atom that has 3 electrons in the outermost shell. So in first case, number of electrons in the system is increased. In second case, number of holes in the system is increased. In both cases, the conductivity will increase. Okay, and there is an interesting.
Why it is neutral or positively charged?
Sorry, void.
So why is it written that the void is positive or neutral?
No, it is written as O, 0, O. That is a way of denoting a void. And effectively, it will be, it is like a hole. It means that now other electrons can occupy this. It will sort of attract electrons. So it behaves as if a positively charged space. Although overall, there is no net charge in the system because the number of electrons and number of protons in the entire this solid will be equal to 0. But now since it might attract electrons, electrons can come here. So it will behave as a positive charge. And if we apply a voltage, positive voltage, for example, in that case, electrons will move in the opposite direction, and this will move in the direction of a positive charge. And so that's why it is like a quasi particle which has a positive charge. The overall system is, however, neutral.
Excuse me, sir.
Okay.
Sir, like we saw that in semiconductors, that hole was like a free energy state in the valence band only. So like it is written that current flow in metals is due to flow of electron, but we see that in metals also there are free energy state in valence band. So shouldn't it be holes in metals also?
Shouldn't it be holes in metals also?
Yes, sir.
Yeah, sorry. Can you repeat your question again, please, about your comparison of metals and semiconductors?
So like in semiconductors, there was some free energy state in valence band, and you said that like those free energy state behaves as holes. So in metals also there were free energy state in valence band. So why they didn't behave as holes?
Yeah, that's a good question actually. The reason for that is that when there is no thermal noise, when at absolutely zero temperature case. So let's go to that slide itself. Uh, these electrons were here. So originally these electrons were bonded to their respective atoms and they were sitting in the valence band. And now at high temperature or at room temperature, these electrons have gained enough energy so that they can be free from their respective atoms and they can go to the conduction band. But in metals, in this kind of metals, for example, all the electrons are, even at T equal to 0 kelvins, when all the electrons are bound to their respective atoms, even then, there are some free states in the valence band. So these free states are not the whole states, like they are in the semiconductors. Do you see this? Do you sort of get it?
Sir, little bit.
Yeah, so the holes come into the picture because at room temperature, electrons have gained sufficient energy and they have moved to the conduction band and they have left behind vacancies in the atoms. But in case of these metals, even at T equal to 0 Kelvin, when all the electrons are bound to the atoms, there are no vacancy in the system. Even then, we have some states in the valence band which are unfilled, which are not filled, like this. So these states in the valence band, these are not because of the vacancies. This is just how it is actually. This is just the electronic configuration of this solid. In semiconductors, however, the valence band was completely filled, and because of the vacancies, it has at room temperature, it has now some empty states in the valence band.
Okay,
Okay,
sir.
so there is a difference. These states are because of the vacancies. These states are not because of the vacancies, and that's why these states are the whole states. These states are not the whole states.
So, sir,
Okay, so I guess yeah,
do electrons leave the bonds in metals also, like in silicon crystal?
yes, definitely. So in metals uh, at for example at room temperature, some of the electrons here at the top of at this, they may go here. So some of these states might be empty and some of these states might be filled. So there will be a continuous sort of flow of electrons from here to here, here to here and back.
So, sir, isn't a hole is created just for a moment only, like, but it is created, and that is also affecting the conductivity.
In semiconductors or in
No, sir,
where?
in metals, like hole was created when electrons was jumped out of the bond. So in metal also it is happening.
Yes, in metal also a vacancy might be created in the bond. But the thing is, in metals, there are so many electrons, the number of electrons which are free for conduction, which are available is huge actually already, which means that almost all electrons in the valence band, they are free for conduction. And so, for example, if there are 100 electrons that are available for conduction and only 5 holes are created, then these 5 are very less in number as compared to this already available electronic concentration. So that's why we generally don't talk about holes in metals.
Okay, sir.
However, in semiconductors, there was nothing available for conductors at 0 Kelvin. But at room temperature, there are now five electrons and 5 holes. And that's why they become important.
Okay, sir.
Okay, and so this essentially, in terms of band structure, it when we do doping, it means that we have now introduced an energy level in the band gap. So I'll explain this in more detail in the next class, maybe. And then we will discuss our first electronic device, the semiconductor junction or the semiconductor diode. Okay, so that's all for today's class. Any other question? There are some questions in the comment box.
Sir, can you please share the PPTs for all the lectures after lecture 2? I don't think we've got them yet.
Yeah. So I'll share up to lecture 5 today itself. Don't worry. So there is a question from Aniket in relative mobility to